and hello, Trino users. I'm Sanghyun Lee, and I'm working as a data engineer at SK Telecom, which is the largest telecom company in South Korea. In this session, I will share how we built the Kappa architecture system and efficiently delivered real-time data to Trino users. The data platform I will cover today is a large-scale Trino cluster serving manufacturing data. Data is generated at 3 million TPS, and the accumulated data size is in petabytes. The Trino cluster has hundreds of nodes, and the cluster executes over 300 queries per minute. And a single query reads terabytes of data on average. Until now, this data has been provided to thousands of Trino users in hourly batch. However, many users wanted to get data as soon as it was generated. So we decided to design the Kappa architecture for this. And I would like to share with you how we did it. Broadly speaking, real-time data architectures can be divided into two categories. Early real-time data architectures looked like something called Lambda architecture, and you have a batch layer and a real-time layer. And the real-time layer provides low latency but less accurate data. To compensate, the batch layer provides accurate but high latency data. Users use a merged view of two layers, and we need duplicate business logic in two layers, and we need to combine the result of two layers back together. This complex design was used because old stream processing engines provided low accuracy. However, modern real-time processing engine provides both high accuracy and low latency. This enables Kappa architecture, which only uses the real-time layer without the batch layer. And we will cover the real-time processing engine layer in detail. So, what are the goals of our Kappa architecture? First, the data must be accurate, which means data must be provided exactly once. Second, data should be served with low latency. And third, it should provide high streaming ingestion performance. Finally, it should provide high query performance. Many enterprise production level real-time data architectures will have similar goals. Let's take a look at the building blocks to achieve these goals. First, we need a place to store the data generated by the data source. We decided to use Kafka, a distributed message queue that is the de facto standard. Since we use heterogeneous data sources, so we decided to use Trino as our query engine. So how do we query Kafka messages on Trino? The simplest solution would be Trino's Kafka connector. With a simple setup, you can query real-time Kafka messages on Trino. And this is probably the simplest real-time data architecture. However, there is a limitation to this approach. It provides only limited query performance. As with any query engine, one of the biggest factors of query performance is predicate pushdown. However, Trino's Kafka connector provides pushdowns only on three Kafka internal fields, which are offset, timestamp, and partition ID. It does not provide pushdowns for the message fields that most users will be interested in. In other words, most queries will perform a full scan. As the data volume and the number of queries grows, system will become overwhelmed. So this might work for ad hoc use, but it can be difficult to use at a production level. As we have seen, reading Kafka messages directly from Trino is not efficient. Instead, we need processing engine to convert Kafka messages into an efficient data format. And we should read this efficient data format on Trino. In conclusion, what we need is a real-time processing engine and an efficient data format. First, let's find the right real-time processing engine for us. Let's compare the most famous and widely used ones, Spark Structured Streaming and Flink. Spark provides two different modes, microbatch and continuous. Spark's microbatch mode guarantees exactly once but has higher latency. Spark continuous mode provides low latency but only guarantees at least once delivery. Unlike Spark, Flink provides both exactly once delivery and low latency. Now, let's look at the Yahoo's famous streaming benchmarks. The x-axis is the percentile of latency, and the y-axis is the latency value. The blue line is 50,000 TPS, and the orange line is 150,000 TPS. Flink on the right reliably provides low latency compared to Spark on the left. Additionally, Spark offers a number of stream processing features that Spark does not. The details are beyond the scope of this session, so let's move on. In summary, if you are not sensitive to latency and only need basic streaming features, Spark is a good choice. However, if latency is important and you need advanced streaming features, Flink may be a better choice. As a result, we chose Flink because we needed low latency and advanced streaming features. Let's go back to our Kappa architecture diagram. As I said earlier, we chose to use Flink as our processing engine. Now we need to decide which data format to use. To choose the right data format, we need to learn more about exactly once delivery. This is because exactly once delivery cannot be achieved simply by using a processing engine that claims to support exactly once delivery. Instead, all the components need to work together. We need three things for exactly once delivery: processing engine, replayable source, and transactional sink. The processing engines guarantee exactly once delivery only for the source and sink that meet these conditions. As you may already know, our data source Kafka is replayable. This is because we can reproduce the message by resetting the offset to the past. So we only need the third condition, a transactional sink. And in this context, sink refers to the table where the data will be stored. So we need a transactional table. Then, what is the transactional table? The transactional table provides what is commonly known as ACID properties. Each user can use a different state of a table. In other words, each user can use an isolated snapshot. A writer's snapshot is only visible to the writer until the writer commits it. The writer either successfully commits or it changes nothing, which means it does not change partially. And the readers can only see the committed snapshots. So I'll talk more about transactional tables later in more detail. Let's go back again to our Kappa architecture diagram. As mentioned earlier, we chose to store our data in a transactional table to achieve exactly once delivery. However, there's one more problem here. It's a small file issue that happens all the time when serving real-time data. So, what is a small file issue? Small file issue is a problem that occurs when processing a large number of small files. Because of the large number of files, Trino coordinator has to create and schedule lots of splits. As a result, this increases the load on the Trino coordinator. Also, because of the because of the small file size, skipping data using index or stat is less effective. In particular, real-time data dramatically accelerates small file issue because we create file frequently to reduce latency. To resolve this, we need compaction. Compaction combines multiple small data files into one large file. This solves the small file issue that I just mentioned. However, compaction job should not interfere with other jobs. In other words, the compaction job should not prevent the processing engine from ingesting real-time data. And also, it should not prevent users from querying the table. Transactional table also solve this problem as well. Transactional table allows different jobs to use different snapshots. As a result, the ingestion job, compaction job, and query job can use different snapshots. So they can do their own job without interfering each other. In conclusion, we solved the small file issue by performing compaction on the transactional table. We'll talk more about compaction later when cover Iceberg. So let's go back to our Kappa architecture diagram. As I mentioned earlier, we use compaction to solve the small file issue. Now let's talk about transactional table in more detail. Which transactional table format can you use, and which one is best to use? These are most widely used transactional table formats: Hive, Delta Lake, Hudi, and Iceberg. However, we cannot use Hive. To write to a Hive table using a transaction, you must acquire an exclusive lock. This means if one user is writing to a Hive table, all other users cannot use the table. Additionally, we think Delta Lake is great, but we have not considered it at this point because we prefer an open table format that is more vendor independent and platform independent. So let's talk about Hudi and Iceberg in more detail. Hudi and Iceberg are similar in many ways. They are transactional table format for large-scale analytical data, and they provide many features for real-time processing, such as atomic writes, snapshot isolation, and so on. So let's talk about the differences. Hudi has two advantages that Iceberg does not have. First, it has lower latency. Iceberg use columnar data files. On the other hand, Hudi use not only columnar-based files, but also a row-based delta files, which provides lower latency. Additionally, Hudi provides an auto-compaction that Iceberg does not provide. So you don't have to write code for compaction, and you don't have to schedule compaction jobs. However, we have some issues with Hudi. First, Trino's Hudi connector cannot read row-based delta files, so we cannot get Hudi's low latency on Trino. Next, in our benchmark tests, Hudi had lower performance compared to Iceberg. As shown here, insert was 9% slower, observed was 40% slower, and query was six times slower. However, performance depends on your environment and your workload, so you can test it yourself. Anyway, we decided to go with Iceberg. This is our final Kappa architecture diagram. It consists of Kafka, Flink, Iceberg, and Trino. Now, let's take a look at how we can fine-tune each component. These are the performance goals for our Kappa architecture that I mentioned earlier. How can you achieve all of these goals? Unfortunately, we cannot get them all at the same time because there's a trade-off here. So we'll talk about what you can get and what we may lose depending on how we fine-tune each component. And also, I will share some guidelines on how I recommend you to set up each component. Let's talk about the following four topics. First topic is low latency is expensive. To fine-tune latency in our architecture, we need to understand Flink checkpoint. At each checkpoint, Flink workers commit records to the sink. Users can only see committed records, so the checkpoint interval and latency are always the same. In other words, short checkpoint interval provides low latency. However, low latency comes with three costs. First, it reduces ingestion performance. More resources are wasted creating checkpoints. In other words, fewer resources are used for stream processing, which is what we actually want. As shown in the figure, Reducing the checkpoint interval from 1 minute to 10 seconds reduces ingestion performance by 70%. Second, this causes small file issue, which reduce query performance. Of course, compaction will eventually solve this, but before compaction, hot data reduce query performance. Lastly, compaction requires more resource because more files should be compacted. In conclusion, low latency is very expensive, so it is best to set it only as low as you really need. More than that wastes too much resource. Let's talk about the second topic, how to set parallelism. Given the same amount of resource, how many workers should we use? Should we use a large number of workers and give each worker fewer resources? Or should we use a small number of workers and give each worker more resources? Ideally, it would be most efficient if you set the number of workers equal to the number of Kafka partitions. But what if there are thousands of Kafka partitions? Too many workers cause two problems. First, as shown in the figure, the checkpoint creation time increases. This is because Flink needs to synchronize the state of many workers. So more resources are wasted on checkpoint creation and fewer resources are used for stream processing. The result is lower ingestion performance and higher latency. Second, high parallelism creates smaller files, which makes the small file issue worse. On the other hand, low parallelism also has its drawbacks. When parallelism is low, a single worker handles more data. As a result, it takes longer to recover from the failure of a single worker. In conclusion, there is a trade-off here again. If ingestion performance and query performance are important, set parallelism to low. Otherwise, if recovery time is important, then set the parallelism to high. Let's talk about the third topic, how to optimize compaction. First, let's take a quick look at how Iceberg compaction works. First, it reads data file list from the most recent snapshot. Next, it groups data files by partition. After that, it regroups the data files into file groups with max file group size or smaller. Next, it reads and sorts the data from each file group. After that, it writes data into new data files. Finally, it creates new snapshot and commits. Next, let's talk about major configurations for compaction. First, I recommend enabling partial commit, which is disabled by default. Compared to a single large commit, multiple small commits are less likely to conflict. Next, apply time-based partition and perform compaction after each partition is complete, because compacting on hot data can cause commit conflicts. Next, sort your data files. Compaction use bin packing by default. This does not sort data, it just combines small files based on file size. So if the data is not stored, file pruning will not work well. This means user queries will read almost all the data files. Lastly, choose the right sort strategy. There are two strategies, basic sort and z-order sort. First, basic sort strategy sorts data hierarchically based on a given field order. To achieve high query performance, choose fields that are frequently used for filtering as sort fields. Second, the z-order sort strategy sorts data by z-value, and it works well when querying coordinate data or location data. How do we choose between the basic sort and z-order sort? Of course, it depends on the nature of your data and query. However, I think the basic sort is better for most use cases, including us. In our case, sort strategy used 80% less time and memory to run the same query. But of course, it is best to test and decide for yourself with your own data and your own queries. Let's talk about the last topic. Why should we expire snapshots? Real-time data creates new snapshots very frequently. Every checkpoint and every compaction job creates a new snapshot. If there are too many snapshots like this, two problems occur. First, metadata becomes too large, which reduces query performance. Second, it keeps too many unnecessary data files. In conclusion, we need to monitor our metadata size and regularly expire unused snapshots. Before we wrap up the presentation, here's a quick recap of what we have covered so far. In the beginning, we compared two real-time data architectures, Lambda and Kappa. Lambda architecture is unnecessarily complex and it is not suitable for modern real-time data architecture. So we chose Kappa architecture. Then we talked about Trino's Kafka connector, which can be used as a simple real-time data architecture, but we don't use it because it only provides low query performance. Next, we compared two most popular real-time processing engines, Spark and Flink. And we chose Flink because we needed low latency and advanced streaming features. After that, we talked about three conditions required for exactly once delivery. We need processing engine that supports it, and replayable data source. Lastly, transactional sync. Next, we talked about small file issue that always occur in real-time data architecture, and we talked about compaction to solve it. After that, we talked about transactional tables which provide ACID properties. And between the two popular table formats, Hoodie and Iceberg, we chose Iceberg for its high performance. Finally, I gave 4 fine-tuning guidelines to build an efficient real-time data architecture. Finally, I will briefly share you the results of our performance test, and then I will wrap up the presentation. We are collecting real-time data with 1 million TPS using 60 cores and 100 gigabytes of memory. And it takes about 4 seconds to run a heavy query that retrieves 2 billion of rows of data. So thank you for listening to the presentation so far. Feel free to ask me any questions. Thank you.
All right, hello. Looks like we've saved some
Hi.
time for Q&A at the end of this session, so if anyone has any questions in chat, feel free to chime them in. Thank you, Sanghyun, for that talk. That was super informative and an interesting design challenge that I don't think I've heard too much similar to that at other Trino events, so it's nice to hear about kind of a different way in which Trino is being deployed. Dave H had a question about the benchmark setup for Hootie versus Iceberg. He says that they've been using Hootie in production for about 3 years with the metadata indexing and column statistics and multimodal indexing. So the question was if those were used in the benchmark or if not.
Actually, we tried to make a similar setup with Hoodie and Iceberg as much as we can. So actually, I cannot exactly remember what the detailed configurations, but I think we did similar setup. So I think our workloads are more fit to Iceberg. So yeah.
Yeah, I think that's
Yeah.
a common conversation and conclusion to benchmarks that I think people often like to overlook is that different things will do better based on different workloads. It's the best way to test whether or not something is fastest for you is to run it with your work, or a representative portion of your work. So, it's Hootie will shine in some places and Iceberg will shine in others. And just because Iceberg shined at SK Telecom doesn't mean that Hootie will not be the ideal choice somewhere else. So I always like to push back against using benchmarks and speeds as the ultimate source of truth for things, because sometimes it's about which one you're better at using. If you're able to configure a certain system better because you have experience with it, that might allow you to get more out of it. Shuo Lee has a question. I'm not sure I understand that one. What Iceberg do you use?
I'm using Hive catalog for Iceberg.
Okay. Iceberg catalog. It was corrected right after.